Today, let's look at improper integrals. We've seen that in integration, if we're finding a definite integral, that was the limit of Riemann sums, and we use the fundamental theorem of calculus to evaluate those definite integrals. Now we want to explore some integrals that don't meet the conditions of what we would normally call a proper integral. So an integral expression in this form, the integral from a to b of some function f of x dx, is going to be considered a proper integral if the limits and the function are bounded. And proper integrals are always well defined. The limit would converge. So we're going to take a look. First of all, there are two types. There's either a or b is infinity. That would be an improper integral. Or type 2, the region defined by the function has an infinite discontinuity in that closed interval from a to b. So those are the definitions of improper. In this first example, we want to sketch the infinite region that lies under the curve of 1 over x squared. And we're going to sketch that so that our lower bound is going to be at 1. So this is the branch of 1 over x squared. And what we're wanting to consider is if 1 is our lower bound, so right here, and we want to know the area under the curve all the way out to infinity. Or to get us started, we're going to just say, let's consider if we find the area up to some value, we'll call that value t. So if we rewrite this, we can take the integral from 1 to t of 1 over x squared with respect to x, and that's going to produce negative 1 over x from 1 to t. And if we evaluate that lower bound and upper bound, we're going to get negative 1 over t minus negative 1. So what does that actually tell us about the behavior of that shaded region? So if we consider some large value of t, we're going to see that the value is really close to 1. So that tells me the limit does exist. And if we evaluate the limit as t is moved further and further to the right, then we have 1 minus 1 over t, and we know that 1 divided by some extremely large number is going to head to 0, so the limit is 1, and we would say that this is a convergent limit. So we're going to see that the improper integral will converge if the limit exists. Otherwise, the improper integral will diverge. And this in case 3, those are case 1 and 2, and we'll see in case 3 that the improper integral requires both of the integrals to be convergent in order for the integral to also be convergent. If either of the two integrals is divergent, then so is the integral. And we'll look at these 3 cases in the lesson. So in this second example, we'll first rewrite this to be the limit as n approaches infinity, and we'll replace that upper bound for our improper integral to n and evaluate 1 over x dx, and then take the limit at the end. So we know that the limit as n approaches infinity of this definite integral would be the natural log of the absolute value of x evaluated from 1 to n. So I don't want to do the limit until I've evaluated the integral. So we have the natural log of n, And since we're starting at 1, we know that the function will be positive. We don't really need the absolute value bars. And the natural log of 1, which is 0. So we're considering the limit as n approaches infinity of the natural log of n, and that would be infinite. And according to our table above in our notes, this was type 1, and it was case 1, and it was improper because x went to infinity, made it improper on the upper limit. This was my indicator. I had an improper integral. So we wrote the limit and used an arbitrary x value like n or t. We integrated, we evaluated, and finally found the limit. So the improper integral diverges because the area is infinite. So this is a divergent integral. In this theorem, this is the P series test. If we have some function in the form of 1 over x to a power, we say it's convergent when that power is greater than 1, and we'll find that it's divergent if the power is less than or equal to 1. So let's give this a look. If you go back to your table, you'll see that this is type 1. So we have an improper integral. So it's a type 1, and it's case number 2, I believe. So we want to rewrite the improper integral as the limit, and this time we'll use t. As t goes to negative infinity, and we're going to go from t to 0, x e to the x dx. So we want to integrate that. And this was, let's see, we'd use, if u is x, then du is 1. And if dv is e to the x, then v is e to the x. So integration by parts is going to give us x e to the x minus e to the x. So we did that by parts. And we want to take the limit as t approaches negative infinity for x e to the x minus e to the x from t to 0. So we'll evaluate this, and then the limit would come last. So the limit as t approaches negative infinity. So we've got 0 minus e to the 0, and then minus, and we're substituting t. So we got t e to the t minus e to the t. And now if we consider as t approaches negative infinity, we have negative 1 here, and then a large number times e to the negative infinity. So that's going to send us to 0, and this would send us to 0. So our limit is negative 1. So the area under the curve converges to negative 1. In example 4, we have infinity at the bottom and the top. So this is example number 3 on our table. So we've got to break it up into 2 parts. Let's break it up from negative infinity to 0, 1 over 1 plus x squared, and then from 0 to infinity of 1 over 1 plus x squared. So we're going to rewrite the improper integral to be 2 integrals, and then we'll consider the limit as, I don't know, we can pick some number. Let's say we pick a goes to negative infinity. So this looks like arctan. And that's going to go from a to 0, And then this one we'll use b. So the limit as b goes to infinity of arctan, evaluated from 0 to b. So evaluating and then finding the limit as a goes to negative infinity, we've got the tangent inverse of 0 minus the tan inverse of a for that first part, plus the limit as b approaches infinity of tan inverse b minus tan inverse 0 for the second part. And this one goes to 0, this one goes to 0, and the angle would be the limit, let's see, it would be pi over 2 and pi over 2 for the remaining pieces. The tan inverse at infinity is going to go, the angle for tan inverse is going to approach negative infinity at pi over 2 in both cases. So we have a convergent limit here. This improper integral converges. It's bounded. We've got an area. In example 5, we want to sketch the function f of x as 1 over radical x minus 2 over the interval from 0 to 5. And that would look like a branch here. We've got a break in the graph. And we're going to use u is x minus 2, and then du would be dx. So at x equals 2, we have this infinite, this is one that has an infinite discontinuity. So we want to consider, why would we start to look at 2 to 5 to be considered improper. So that would be at x equals 2, f of x has an infinite discontinuity. And that was back in our notes, that was the type 2. So if we solved the integral and renamed it s of t as the area goes from t to 5 of that function, we can use this substitution and integrate 1 over u to the 1/2 power du. So I'm not going to put the limits there just yet because we're going to revert back to our x minus 2. So that's going to give us 2x minus 2 to the 1/2 power evaluated from t to 5. And then we want to find the limit of that. So this would be substituting our 5. We got 2 square roots of 3 minus 2 square roots of t minus 2. So we found the value of the integral, but now we need to evaluate the limit as t approaches 2 from the right. And remember why we're doing from the right is because we have that infinite break in the graph at x equals 2. So 2 radical 3 minus 2 radical t minus 2. So as t moves to 2 from the right, this is going to go to 0. And our limit is 2 square roots of 3. So this one converges. Notice how I'm evaluating the limit at the end. Don't get ahead of yourself. Whoop. And then here's the definition of improper integrals, the type 2 kind. We saw this earlier. And I'll let you read these things for yourself. We'll just model them here in our last 2 examples. So in this case, we want to look at the limit. And I'm going to use a again. As a approaches 0 from the right, because consider the natural log of x. As we approach 0, as x moves to 0 from the right, y is unbounded downward, so we're thinking about that. So we have a to 1, natural log of x dx. So you got to think about this, that natural log function has some problem at 0. So we have to think about the right-hand limit. And then, again, by parts, integration by parts, we have if u is natural log of x, then du is 1 over x. And if dv is 1, because I'm considering this to be times 1, then v is x. So we have integration by parts, u times v is x, natural log of x, and then we want to evaluate x times 1 over x, which is 1. So we have the limit, don't have enough room here. I'm going to use the limit last. The limit as a approaches 0 from the right. And we're going to take care of this. So we have the limit as a approaches 0 from the right of x, natural log of x, minus the integral of 1, which is x, from a to 1. So the limit as a approaches 0 from the right. So we considered our graph. We used integration by parts. We wrote out the integral, and we're going to evaluate it. Then last, we'll take the limit. So substituting 1 in for here, we got 1 and then substituting a, we have a, natural log of a, minus a, because this went to 0, that left negative 1, substituting a, and a, and then finally taking the limit. So the limit as a approaches 0 from the right would give us negative 1, and this is going to be 0, and this is going to be 0. So we have a convergent improper integral. The area converges. And then our last one, what do we know about the graph of 1 over x minus 1 from 0 to 3? So we want this graph, x minus 1. It's discontinuous at 1. So we have case 3, because the graph is discontinuous at 1. So we've got to break that up to go from 0 to 1, 1 over x minus 1 dx, and then we can go from 1 to 3 of 1 over x minus 1 dx.